we're getting into chapter 3, which is talking about functions, and we're going to talk about graphing functions, different techniques to help us to graph those functions. But first, before we talk about functions, we need to know what a relation is. And so a relation is a correspondence between two sets let's call it capital X and capital Y. Where X is called the domain, and Y is called the range. So in a relation, every value in X has to correspond with exactly one. Exactly one would be if we were talking about function. But if we're not talking about function, which we're not, we're just talking about a relation, so this could be different. So X has a correspondence with at least one value in the range. So when we've been dealing with equations and we pop values in and we plug a value in for X and something comes back out for Y, that's a relation. And so points, a lot of times, can be written in the form of where you're putting in your X value, and then your Y value is written the same way as f of X. Okay, so there's a couple ways. Relations are special if they're functions. So we say a relation is a function if for every value of X in the domain, it corresponds to exactly one. In the range. Okay, so for every X, we're only getting back one Y. So looking at relations to see if they're functions or not, there's a couple different things that we can have. So we can have a set of points or not. So let's say we have the following. So find the domain and range of each relation, then determine whether the relation represents a function. Okay, so let's say we have fathers over here. And we have daughters over here. And we have Bob. And Bob, Beth, and there is Diana. And then there's John. There's John. And his daughter is Linda. And there is Chuck. And his daughter is Marcia. So looking at this, you should be able to tell what the domain is and what the range is. The domain are the fathers. So in this set, we would have Bob, John, and Chuck. And the daughters. So that is the range. Which would be Beth, Diane, Linda, and Marcia. So the question is this a function? Why or why not? Anyone want to chime in?
It's not because Bob had 2 kids.
Right. So because of one input, one person in the domain, there is 2 separate outputs. Okay, because of this, because of Bob, like you said, this is not a function. Okay, so no, because Bob, he has 2 outputs. He has 2 daughters. Okay, so what about this relation where the level of education depends on the income that you would get? The level of education, and then we have average income. And so if you had less than 9th grade, it's telling that the average income is $18,120. If you had between 9th and 12th grade education, then your average income would be $23,251. High school graduate, then $36,055. You have just some college. You guys are all following in this now. $45,800. $810. And a college graduate is $67,165. Okay, so the domain and the range. So which one is the domain and which one is the range? The domain, that's what we're putting in, and depending on what your level of the education is, depends on what you're going to get back. And so our domain is going to be the level of education. And I really don't want to write this. So level of education. And the range is the average income. Notice that every input is giving us just one output back. So, is this a function? So less than ninth grade, right? That could be 8th grade or 7th grade. That would be telling me I'm getting $18,120 for those 9th through 12th. So 9th, 10th, 11th, or part of 12th grade, you're getting $23,000. So after high school, you're getting $36,000. If you decide to go to school, some more. So would this be a function? To your right, it is a function. Shaking your head, I saw it. Let's see. Okay, so yes, it is a function. Even though really could be multiple inputs that give us the same output. It's just that every input that we decide is only going to give us back one output. And so this would be yes. Every input is exactly one output.
So if we had written it the opposite way and put in average income to get out the level of education, it would not be a function, right?
Yeah, correct. So you're right. So if it was opposite, I said, okay, we're looking at average income and then looking at the average income, what could the level of education be? You're right, because there could have been multiple for like $18,120. You could have had, like I was starting to see if I could trick you. You could have the 8th grade, the 7th grade, the 6th grade. And so one input there would have given us multiple outputs. And so that would not be. So sometimes instead of just a lifetime scenario, they might just give you points and ask you, is this set of points a function? And so if we had the set of points, let's say 0, -2 is a point, 1, 3 is a point, 2, 3, and 3, 7. And again, it's saying find the domain, the range of each of the relation, determine if the relation represents the function. So we can do the same thing we just did, or how it was set up, where we have our input or our domain and our output. Let's just kind of map it. So to each point, so like 0, this is mapping to the y value of -2. If I put in 1, this maps to the y value of 3. If I put in 2, this also maps to 3. And then 3 would go to 7. So our domain is our input, so 0, 1, 2, and 3. And our range, which is our output, would be -2, 3, and 7. And so would this one be a function? Why or why not?
Wouldn't it not be a function because the range still only has 3 outputs for the 4 inputs?
That's a good point. What do you guys think, Kimmy?
It's a function, correct?
And so why do you think that's a function?
Because every input has one output.
Okay, so we got countering arguments. So on the participant, if you click on participants and then just go down and either tell me yes, you think it's a function, or no, you don't think it's a function. You had a 50-50 chance if you don't know. So 9 votes out of 35. There you go. 10 votes out of 35. Okay, so 14 of you. Not even half the class yet.
I don't see a way to vote.
Okay, so if you take your mouse and you hover over the screen, you should get a toolbar that comes across that says, you know, the video. One of those share screen. One of those should say participants.
Oh,
Click on participants. It brings all the names of everybody in the class, and then you'll see the yes or no below the names.
awesome. Thank you.
This makes it feel so much more like a class, being able to see your faces. Thank you. Okay, well, 14 say yes, 4 say no. 18 people, that's half of you, a little over half. And so those of you who said yes is right. And it's okay that 2 separate inputs give us the same output. It would not be okay though if this was swapped where 3 gave us both 2 and 1. That would not be a function because 1 input in that case would have given us back 2 outputs. But in this case, every input, because 0 only goes to -2, that's 1 output. 1 just goes to 3, that's 1 output. 2 just goes to 3, that's 1 output for 2. And 3 goes to 7. So every input has 1 output. So I tend to, if it gives me points like that, I tend to like just to do my mapping just to see if there's any X value that's going through more than 1 point or more than 1 Y value. One more like that. So let's say you're given the set of points and the following is -4, 4. -3, 3 is a point. -2, 2. -1, 1. And -4, 0. Our domain, those are all our x values. I got -4, I got -3, I have -2, I have -1, I have -4 again. I don't have to write that twice. And then my range, I have my y value of 4, 3, 2, 1, and 0. Thing is that -4 goes to +4. 3, 2, 1. Okay, so -4 goes to +4. But over here, this -4 also goes to 0. -3 goes to 3. 2 goes to, or -2 goes to 2. -1 goes to 1. Okay, I just labeled those. So yes, a function, no, not a function.
Is it not a function?
So why wouldn't it be a function?
Because the 4 has 2 outputs.
Right, so the -4 has 2 outputs.
I'm going to say it is a function because the second output is 0, which is not a number. It's a. I'm going to say it is a function.
0 is a number.
It's a lack. It's like white. It's a lack of number.
Yeah, we consider 0 a number. So no, it's not, because that x equals -4 is 2 outputs. And they were 4 and 0. Okay, so if you're given an equation, you should also be able to see if that is a function or not. Actually, before we do that, you should be able to look at function notation and find the following. Say you're given f of x is equal to the equation -2 x squared plus x minus 1. So if it said to find f of -1, what is that telling us to do? So we're going to plug in -1 wherever we see an x. of x. This is not saying I'm taking my function and multiplying by -1. It's saying I'm going in here, and wherever I see an x, I'm going to, so I have a -2, I'm going to put parentheses. And then that parentheses is squared, plus I see an x, I'm going to put parentheses, and then -1. Go in, let's put in -1, wherever we had written those parentheses, and use order of operations to simplify. So exponents come first before multiplication. So -1 quantity squared is +1. So I have -2 times +1 plus a negative is really minus. So -1 minus 1. Multiplication comes before addition or subtraction. So -2 times 1 is -2. -1 minus 1. -2 minus 1 is -3. Minus 1 is -4. So this is basically saying we have a point on that graph when x is -1, y is -4. So part B, look at if it told you to find f of -x. We were actually doing this piece before when we were looking to see if things were symmetrical across the x or y axis. So if we plugged in -x wherever we saw an x and we got the same equation back, changing our x values reflection across the y-axis. Same sort of idea, we're just going to go in and wherever we see an x, let's put parentheses and we'll go back in and plug in -x. We have -2, parentheses, and then x, or sorry, not x, that squared, plus you see x, so put parentheses -1. We get -2, well, -x times -x, another way to write that is just x squared, plus a -x, so minus x. We can't take this any further. There's no more like terms, no other way to simplify it. So this would be f of -x. It told us to find -f of x. This is just saying another way of saying let's multiply our whole function of f of x by -1. So this is like a negative outside our parentheses. And then our equation, which is -2 x squared plus x minus 1. We need to distribute this negative to each term inside the parentheses. And so we get back negative times negative is positive, so 2x squared. Negative times positive, so minus x. Negative times negative is positive, so plus 1. I'll ask you to find f of 4x. Same sort of idea. Go in, put in a parentheses wherever you see an x, so -2, that parentheses, and then square it. And then it was plus x, so plus parentheses, and then a minus 1. Sometimes you're plugging in numbers, sometimes you're plugging in variables or expressions. And so here, same sort of idea, just go through and let's simplify. So you have -2, but 4x times 4x, that's actually 16x squared. Plus 4x minus 1. And -2 times 16 There's no plus or minus in between the 16 and the x squared. So we're just multiplying the negative 2 times the 16, which is negative 32. X squared plus 4x minus 1. One more. What if it said find, actually let's do two more. F of x plus h. So we're going to go in, so negative 2, we're going to put in a parentheses where we're seeing x, but make it big enough so we can put in x plus h. So parentheses squared minus, actually plus, seeing x, so put parentheses. Minus. Plug in x plus h wherever you see parentheses, and then simplify. So negative 2, we need to multiply out x plus h times x plus h. Technically, plus, this is 1 times that parentheses. I really don't need those parentheses there. So plus x plus h minus. If we FOILed out x plus h times x plus h, we get x squared plus 2xh h squared. Down plus the x plus the h minus the 1. And now distribute the negative 2 to every term inside that. So if we do that, we get negative 2 times x squared is negative 2x squared. Negative 2 times 2xh, so that's minus 4xh. Negative 2 times h squared is negative 2h squared plus x plus h minus. No other like terms in here. We can't simplify it any further. Okay, so that brings us to an important piece, and you'll use this a lot when you get into calculus. I'm going to kind of go through why in a second. So this is the difference quotient. So the difference quotient says that you have f, you're going to plug in x plus h wherever you've seen x in your function, minus f of x all over okay, so let's use the difference quotient. Let's say we have f of x is given to us to be x squared plus 2. And we want to find the difference quotient of f. If it helps you, do it in pieces and then put it together. So we could, if we wanted to, look at this first piece and figure out what is this f of x plus h. So if I go in and I go and plug in x plus h wherever I see an x in my function. So this is equal to 3. Let's go and just put parentheses first. So we have an x, so let's put parentheses there and square it. So let's simplify this. This is equal to 3, all times the quantity x plus h times x plus h. And then plus 2. So this is 3 times, if we distribute it out, x plus h times x plus h. This gives us x squared plus 2xh squared. Down there, plus 2. Almost there, distribute your 3. So 3 times x squared is 3x squared. 3 times 2xh, that's plus 6xh. 3 times h squared, that's plus 3h squared. And then that plus 2. Now if we look at this minus f of x. Careful, because it's really, if we do that that way, it's like there's a plus in here. If I look at negative of what my f of x function is. Basically, I'm putting a negative out front, and I'm multiplying it to my whole function, which is 3x squared plus 2. If we distribute our negative sign, we get negative 3x squared minus 2. Let's put it all together. I said what you're looking at f of x plus h minus our f of x. And then it tells us to put the whole thing all over. Okay, so purple was our f of x plus h. So this was our 3x squared plus 6xh plus 3h squared plus 2. Minus our f of x, which we found to be minus 3x squared minus 2. And we're going to put this whole thing over h. Combine my terms. Notice you have a 3x squared minus a 3x squared. Those go away. We have a positive 2 minus a 2. Those cancel out. So really all we're left with in the numerator is 6xh plus 3h squared all over h. But I see I have 2 terms in the numerator that have an h in it, so I could actually factor that out of those 2 terms. That would leave me with 6x plus 3h all over h. Things actually simplify further where the h's cancel in the numerator and denominator, and you're left with just 6x plus 3h. It can look kind of ugly and tedious, but really a lot of times they just fall out nicely where terms cancel out with one another, and it comes out to be a nice expression. So
Should it be like that every time you solve it?
Sometimes it's not, unless we manipulate it, and I don't think that we have to manipulate it too much. But if we have a polynomial, yes,
Okay.
it would. And this right here, this is part of one of the main concepts, this difference quotient in calculus, which is basically the derivative. part of the definition of a derivative, which basically tells us we can find the slope anywhere on a curve where it exists differentially. So let me just kind of give you the background behind this, because we're does it later anyways. So let's say you had some function, and let me just draw any. It doesn't matter what the graph looks like. So I'm just going to. Let's say we arbitrarily choose 2 points on here. So let's say we choose this value here, x. So basically this point here, y value is my f of x value. Let's choose some point kind of close to this. Let's call it, but let's give it a distance of, let's say, h. And so this point right here, I would say this is the same thing as x plus h. I look at my y value at x plus h. This is f of x plus h. We looked at finding the slope between 2 points on the line. So if I join those 2 points on the line, the slope is our average rate of change between the 2 points. So if I wrote this out, I have 2 points again. You have the point x, f of x, arbitrary, and we have the point x plus h, and then the y value is f of x plus h. But if we find the slope between those 2 points, the change in your x value or y value, our y value is f of x plus h minus the other x value or y value, sorry, which is f of x, over x value. I started with f of x plus h. I'm going to start with x plus h down here, minus my other x value, which was x. Notice that numerator, we can't simplify it. It's f of x plus h minus f of x all over. Notice x minus x cancel, which is h. This right here, this line that joins these 2 points on the line, this is called the secant line. And the slope of the secant line is the average rate of change. Average rate of change. Okay, so the concept is with behind calculus is that we've only been able to find slopes of lines that only slopes of lines. But if we took this picture right here and instead of doing this value of h this big, we decided to do h smaller. So let's just keep on making h smaller and smaller and smaller as we get closer and closer to x. And so basically what we're trying to do is we're trying to treat this value of h. We're going to let h go to 0. So what's happening is, if I can do the same curve, let's see. If I choose, why do you keep doing that? So instead here, this was our f of x value. I got this x plus h a lot closer. Then that point would be right here, but I could even get that point even closer. It could be right here. And as I get closer and closer and closer, I'm getting a better and more accurate idea of what is going on exactly at this x value on the graph. H goes to 0. You can find or on this. You don't really need to know this, but this is the whole idea behind this. This is called the tangent line. When we get it exactly that slope at a particular point on that line. We can get that exact slope at a particular point on that line by shrinking that h value down until it goes to 0. And so that's why this difference quotient is so important to be able to do. So I may have my calculus students today rewatch this portion if they're struggling with the difference quotient. Because we're going over derivatives right now. Formal definition. Okay, so this is like a main thing again. F of x plus h minus f of x. Okay, so let's say it wasn't a polynomial. Let's say you want to find the difference quotient, and let me make them a little bit harder. Let's say it was a rational function. So f of x is equal to 5x all over x minus 4. Find the difference quotient of x. Again, if it helps you, break it down into pieces, and we need to figure out what f of x plus h is. We're going to go into this function, f of x, and wherever we see an x, we're going to replace it with x plus h. Let's just put parentheses wherever we see the x first, so 5, you see it with parentheses. Denominator, you see an x, so replace it with parentheses minus 4. Let's simplify this down a little bit. And so this is equal to, I can distribute my 5 parentheses in my numerator. So this would give us 5x plus 5h all over. I technically don't need this parentheses around this x plus h, so I can drop it. So x plus h and then minus this 4. There's one piece. We need to figure out what minus f of x is. just putting a negative out front. So this is times negative times quantity 5x all over x minus 4. So putting it all together, we have the f of x plus h, which we just found was 5x plus 5h all over x plus h minus 4 minus 5x all over x minus 4. And then we put this whole thing all over. So we need to simplify this. We normally don't like fractions within fractions. I chose this because I knew I would get a complex fraction back. And so there's a couple ways to handle complex fractions. I tend to like to multiply this by the fancy 1 in order to clear my fractions. And so you can look at all the fractions within the main fraction. So there's only 2 fractions within this main fraction. And we're trying to find the least common denominator. If I can find the least common denominator and I can multiply this by a fancy 1, I could clear my fractions in that denominator. And so our LCD here is x plus h minus 4. And x minus 4. Don't have any common factor together, even though x minus 4 is part of each. So I'm going to multiply the top by x plus h minus 4 times x minus 4. It helps you put that over 1. And then I'm going to multiply the bottom by the same thing, x plus h minus 4, all times x minus 4. Do that, you have 5x plus 5h all over x plus h minus 4. Multiplying, I have to distribute. So this is all times x plus h minus 4 times x minus 4 minus 5x all over x minus 4. Distributing my LCD. This piece, we have, again, x plus h minus 4 times x minus 4. And this is all over just one term on the bottom. So h times x plus h minus 4 minus 4. Usually I don't write this step out, but I'm just showing it this one time. Usually when I distribute, I know what's going to cancel and what will be left. And so notice here our x plus h's, or x plus h minus 4 is going to cancel both of these. So you're left with just the numerator, that first fraction in the numerator, 5x plus 5h, all times the piece of the LCD that didn't cancel, x minus 4. This other piece, this x minus 4, and this x minus 4 cancel. I'm left with a negative 5x or minus 5x. It's the piece of the LCD that didn't cancel, x plus h minus 4. We are not going to distribute the bottom. That's usually a trick, is not to distribute the piece that you're trying to, that you weren't trying to manipulate. So we have h all times x plus h minus 4 all times x minus 4. I cannot cancel factors because of this minus in between the groupings on top. So we actually have to start distributing. 5x times x, that gives me a 5x squared. 5x times negative 4 is minus 20x. Distribute this 5h, so 5h times x, that's plus 5hx. 5h times negative 4, so this is minus 20h. Distribute the negative 5 to each term. Second parentheses in the numerator, we get negative 5x times x is minus 5x squared. Negative 5x times h, that's minus 5xh. And then negative 5x times negative 4, that's negative 20x. And this is all over denominator of the h, all times the x plus h minus 4, all times x. Once again, when we start combining things in the numerator, things start falling away. So this minus 5x squared, I'm sorry, positive 5x squared and the minus 5x squared cancels. I see an error that I just made. This negative 5x times this negative 4, that's a positive 20x. And so notice this negative 20x here and this positive 20x cancel. I have a 5hx and a negative 5xh, which are the same thing, so those cancel. And so in the numerator, you're just left with that term negative 20h all over this denominator, h, x plus h minus 4, x minus 4. Notice that now we have strictly multiplication. We can cancel out those h's. And this simplifies to negative 2 all over x plus h minus 4.
It's supposed to be 20, not a 2.
Yep, you're right. So minus 20h. And I canceled out the h, so it's minus 20 all over x plus h minus 4 and then x minus 4.
Can you scroll back up and show me where you got the negative fx value that's in light blue?
Yeah. Our original equation was f of x is equal to this 5x all over x minus 4. And so basically this piece right here, this negative f of x, is all it's saying to do is put this negative in front of our function.
Okay, I got it. Thank you.
I think this is probably a good spot for a break. There are a couple of things probably should still talk about in this section, so I'll do that. But the next section is pretty short. It's just looking at graphs and looking to see, is it a function or not? And I'm trying to let you see everything in here. So let's take a 10-minute break. We just looked at functions, the difference quotient of a function. Now we need to, there's a lot of different information after looking at the domain of a function. So finding the domain of a function. So when I go to find the domain, I actually go and I look for my trouble spots. Things that would not give me, things that are undefined, or things that would give me back an imaginary number, not a real number. And so finding the domain, you want to exclude the following values. So we're going to exclude values that either set the denominator equal to 0, we need to exclude any values that give us a negative underneath a even powered radical. So exclude numbers that give you a negative number under even. So for instance, if you have the nth root of some function underneath, let's say g of x, then what we need is an n is even. If it's odd, it doesn't matter. You can have negatives underneath the radical. You can raise something to an odd power to get a negative. So if n is even, you need to set g of x greater than. And then later on, we'll be looking at, you have to exclude values when we're dealing with log functions. But right now, we're not doing logs, so we'll skip that. So really, right now, the only things we have to worry about is if you have a rational function or you have variables in the denominator, you got to exclude those numbers that set it to 0, or if you have a radical. If there's no variable in the denominator and there's no radical.
Your audio is like, I think you might be covering the speaker or something.
Okay. So I'm cutting out. And I think, oh, if I talk slower, it will just get better.
It just sounds like you got lower.
Yeah. Maybe because I was going, I don't know. Okay. Maybe it's because I was talking faster and I was, okay. But anyways, is this better?
Do you think maybe the microphone is unplugged? Because I remember you had a microphone at one point that made it better.
We're plugged in.
I don't think it's plugged in.
Did I even start recording? We're having some audible difficulties. Hopefully it gets better. So we're looking at the domain of a function, and when you're finding a domain of a function, you're looking at excluding different values that makes the function undefined or gives you back an imaginary number. So let's look at a couple of examples. So if you were trying to find the domain, let's say h of x, and h of x is equal to 2x all over x squared minus 4. So looking at this, I notice I have a rational function, so I'm going to have some problems when I have my denominator equal to 0. So I know that x squared minus 4 really can't equal 0. We can solve this a couple different ways. We can factor it, set each factor equal to 0. So I'm looking at when this is the difference of squares, so this factor is x minus 2, x plus 2, not be 0. So x cannot be 2 and x cannot be negative. So for our domain, it's going to be all real numbers but that. And so it depends on how they ask you to write it. But if I look at this, I basically have an open circle and shaded everything to the left of -2 to be part of our domain, everything in between -2 and 2 is part of our domain, but not including 2, and everything to the right of it. So our domain, a lot of times we like to write things in interval notation. So interval notation, we're looking at all the values to the left of -2, and so we express that as negative infinity, comma, going to -2, and the parentheses tells us we're not including that in value -2. And then we have a union. So our union means we're taking that set plus this other set. So we're starting at -2, we're really close but not including it. And then we're going to +2, not including it, so parentheses, and then union, we're going from everywhere from 2 to infinity. So this is how we would write this in interval notation. They might ask you to put it in set builder notation. So set builder notation, you would have a curly bracket that kind of denotes set. We're going to put X in here. This vertical line. And then we put in the rules here. So basically, X, this vertical line reads such that. Instead of X such that, X does not equal 2, or X does not equal 2.
Professor?
Question?
Yeah, I want to know, when we're answering that, is it okay if we just do +or -2, or do we have to do it like that?
I'm okay with the X cannot be plus or minus 2.
Okay, thank you.
Let's say you had f of X and f of X is equal to the square root of X plus 3 all over X minus 4. Let's find the domain. There's a couple problems that we would have. We cannot have a negative underneath the square root. And so I noticed that what's underneath the square root, this x plus 3 has to be greater than or equal to 0. So solving linear equations, but subtract 3 on both sides. So x has to be greater than or equal to -3. So this has to hold true. And it has to hold true that our denominator is x minus 4 not be equal to 0. So if I add 4 to both sides, x cannot be. We got to be careful. Both of these things have to hold true. If I was looking on the number line and I was looking at, okay, everything that is bigger than -3 or including, that would be a solid circle, or we can denote including with a bracket. And I tend to like usually put the bracket or parentheses here because that's how we would write it with the interval notation. But then we're going everything to the right, bigger than -3, but we have to stop once we hit 4 because we can't include 4 here. And so I'm going to put a parentheses on the 4 value, and then another parentheses going the other direction on the 4, because then I can have everything bigger than this 4. So interval notation, the domain, we're going to start at -3 and we're going to include it, always moving with your x values left to right. These are denoting x values. So starting at -3, including it, use a bracket, comma, we go all the way up to 4, but not including it. So really, really close on the left. Union, now we're looking at everything to the right of 4, not including 4. So 4, parentheses, 4, comma, infinity.
I have a question. So how come on this one, we only use 2 points or whatever, and then on the other one we use 3?
So, because of what it was and what the stipulations was. And so on our other one, there was 2 values we had to exclude, and so we had to go up to each piece. And so basically with this one, we had to get everything to the left of -2. Then we had to get everything in between -2 and 2. And then we also had to get everything bigger than 2. And so that was like 3 separate sets that we had to put together. Where in this case, we were looking at everything between or bigger than or equal to -3. We just had to exclude this value in 4 here. So if there had been another value that we had to exclude, we would have had more intervals. Like let's say there was something here. We would have had 1, 2, 3 separate intervals.
Okay.
Value here I had to exclude, I'd have 1, 2, 3, 4 different intervals. So it really just depends on how many values you have to exclude and how many pieces we have. If this had just said, if we didn't have that denominator and we just had f of x equal to the square root of x plus 3, then for the domain in this case, it's just going to be everything bigger than or equal to 3. Because we don't have to exclude out that 4 that set the denominator equals 0 on the other piece. So this would just have -3. So in this case, that there's only one interval that is part of the domain. The properties of functions. And this is pretty much just notation-wise understanding. If you have parentheses, you have an f plus parentheses, or sorry, plus g, and parentheses, and then parentheses x. This is all it's saying is you're looking at your function f of x and adding it to your function g of x. The way this is a funky notation because it looks like you're distributing x to each piece, but you're not. Okay, we're going to take our equation, what we have for f of x, and we're going to sum it to whatever the equation is for g of x. So same idea, if there was a minus sign in between that f and g, so f minus g of x. Here we have f of x minus g of x. So just in this case, you need to be careful. Parentheses around the whole equation of g of x. Just like when we were looking at that difference quotient, we were looking at negative f of x, we had to put parentheses around that whole equation. you need to distribute that negative to each piece. Multiplication, so if you're going to multiply two functions together, basically you have just this tiny little dot in between. So f dot g of x, this is telling you you're taking your equation f of x and you're multiplying it to your equation of g of x. And the last piece, if you have f in the numerator divided by g in the denominator of x, this is saying you're looking at your function of f of x and dividing it by your function of g of x. G of x equals 0. So if you are looking at the domain of these properties, the domain of the operations, like f of x and g of x, equal to the domain of f of x intersection which means what they share in common. The domain of f of x with the intersection of the domain of g of x. Only case that you have to be careful of is if you have division, and again, you have to exclude any values which sets that denominator equals 0. The symbol for intersection, you might see it as that upside down kind of V shape. Just telling you that you're taking an intersection of two sets. So if f of x, let's say, was equal to the square root of x minus 1, and g of x is equal to the square root of 4 minus x. For the given function f and g, find the following. Let's say our A said find f minus g of x. Well, all this is telling me to do, this is equal to my f of x function minus my g of x function. Well, my f of x function, that's just the square root of x minus 1, minus my g of x function, and my g of x function is the square root of 4 minus x. In order to combine radicals, though, there would have to be the exact same thing underneath the radical, and they're not, and I can't manipulate it to do so, and so that's as far as you can take it. Minus g of x is equal to square root of x minus 1 minus the square root of 4 minus 1. I'll get 1 is the domain of it. So I gotta look at different pieces. I know that what's underneath this radical, this x minus 1, has to be greater than or equal to 0. And, or intersection. The piece underneath the second radical, 4 minus x, also has to be greater than or equal to 0. So let's solve each one. So I know that here, if I add 1 to both sides, x has to be greater than or equal to 1. If I add x to both sides here, I get 4 is greater than or equal to x. Kind of like my variable on the left, so I'm just going to rewrite it, keeping the sign facing the same way as it is above. So the less than is towards the x, so x is less than or equal to 4. So if I look at this, it has to be what they share in common. So for this piece, x is greater than or equal to 1. I'm going to shade it above. That would be everything to the right of 1. And if I looked at the second inequality, x is less than or equal to 4. If I find 4 here, it's telling me I would include 4 and shade everything to the left. So if I'm looking at what they share in common, where they would overlap in the shading, the overlap in the shading is everything that is falling in between and including 1 and 4. So our domain is going to be -1 to 4, and there's bracket on both sides because you're including those. That's integral notation. You could write it as -1 is less than or equal to x, is less than or equal to 4. That's inequality notation. Write it in set folder notation. So set x, vertical line, such that -1 is less than or equal to x. Say the same exact thing. Just so that I touched on it. If you had a number there, so let's say part C was find f minus g instead of x,
It's not saying.
they had an already 0. Yeah,
Isn't it 1, not -1?
right. Where is it? The -1 coming from? And then f minus g of 0. All you have to do is go back in to your equation f of f minus g of x. F minus g of x. We saw that this was the square root of x minus 1 and minus the square root of 4 minus x. So we want to go back into this equation that we found. We want to plug in 0 wherever we see an x. And so if we do this, equal to square root. And this is where I'm going to have a problem, right? Minus the square root of 4 minus. Here I'm getting an imaginary number. And if I look back up, and this is I chose 0 because when I flipped it originally, I think it was -1 before. 0 is not our domain. Let's actually choose one that is in the domain. So what about 2? We'll forget up to minus b of 2. This will equal the square root of c and x there, so we're going to plug in c, minus 1, minus the square root of 4 minus c and x there, so put in 2. Simplify, we get the square root of 2 minus 1, or the square root of 1 minus the square root of 4 minus 2. Square root of 1 is 1 minus 2. So an input fish fell in our domain gave us a real number back. And I'm just going to leave it in this exact form, but I could put it in a decimal form. Okay, so we pretty much touched on all of chapter 3.1 today. And like I said, the other 2 or 3 sections following this are a lot shorter and not as much information in it. So we'll probably, like I said, pick up the pace on Thursday and get through hopefully 2 or 3 sections.